Hi, grade ninths. Today we're continuing to look at this key features of linear relations that we've been talking about for a while now. We've kind of covered most of the key features. We know about independent and dependent variables. We know what we mean by the initial value and the rate of change or growth rate of a linear relation. And we're just going to finish up by talking about how do we find values of the independent and dependent variables if we're given an equation, a table, or a graph. So that's the last thing here in this list of using key features or finding key features. So if we want to find the value of the independent variable using a table, or the independent variable, the dependent or independent variables using a table, then we extend the table or we read from it. So if the values that we're interested in are already in the table or between the values of a table, we can just read from it or estimate. And if we need to extend the table forwards or backwards, we can do that. From a graph, we sometimes also have to continue the line forwards or backwards. And then once we've done that, we can interpolate, which means read between the points on the graph, or extrapolate, which means reading beyond the graph by extending the line. From an equation, which is usually what students found the most difficult part, we can substitute values if the equation is, or if we're trying to find the dependent variable, because the dependent variable is already isolated in an equation of a linear relation. But if we want to find the independent variable, which is really what this video focuses on, we have to isolate that variable first. And so I'm going to show you an example of that again in this graphic organizer that we've been working on. So in this part of the organizer, we've already taken a look at this. We looked at partial and direct variations here. And then this was the equation. So I'm just going to show you from the equation how to find the value of the independent variable, if that's what we're trying to find. If we're trying to find the dependent variable here, we've already got an equation for the dependent variable. The dependent variable is already here on its own, it's isolated. So all I have to do, and I've written it here, is to substitute a value to find the dependent variable. Just substitute it in here for the independent variable and use the equation to find the dependent variable. That's not too difficult. But if we want to find the independent variable, then we have to rearrange this equation to isolate the independent variable to get the independent variable on its own. So in this example, the way we would do that is I'd first of all get rid of this number here, this minus 20 or negative 20. And the way we do that is by using what we call reverse operations. The opposite of subtracting is adding, so I add 20 to both sides of the equation. So I add 20 to the left side and I add 20 to the right side. That keeps the equation still balanced. But this negative 20 plus 20 is going to make 0, which eliminates that negative 20 from the right hand side of the equation. Once I've got that, and it's written here in blue, then I would divide both sides by 17 in order to isolate the independent variable. So I would get the independent variable on its own here, and then that would be equal to the dependent variable plus 20 and divided by 17. Why do we add first and then divide? That's because we use BEDMAS, but since we're doing reverse operations, we use BEDMAS in reverse. So we do the adding and subtracting part first before the multiplying and dividing part over here. So that's kind of the process for finding the independent variable from an equation. And then in today's class, we did an activity where we practiced that skill. So here is that activity. We are given a problem where we have 4 different people and they work delivering advertising flyers, and there's a relationship between how much money they earn, their earnings in dollars, that's our dependent variable there, E, and the number of flyers delivered in a day, which is the independent variable. But they're given in different forms. So Abby's just given in words, Bob's relation is given in as an equation, Craig is a table of values, and dollar is a graph. So we're going to learn how to find values of both the independent and dependent variable using these 4 different ways of representing variables. You'll see I've already added some annotations to the table there, and you'll see why in a moment. So the first part asks us to find the value of the dependent variable, the earnings, using the 4 different approaches, and the condition that we're given is that they deliver 500 flyers in one day. So how, given these 4 different representations, would we find out their total earnings? So for Abby, what we would do is we would just use logic. We'll use logical reasoning. We're told that Abby earns $25 as a flat fee, so we know she's going to earn this $25 here, and then we're told that she earns 9 cents per flyer. And if I change 9 cents into dollars so that we're adding dollars to dollars, 9 cents would be $0.09. And if we multiply that by 500, we get $45. So her total earnings would be $70. Kind of makes sense that we would just use our logic to solve it with when we have it just written in words. For the table of values, what we can do is we can extend the table of values. So you can see here that the table of values only goes up to 300 flyers, but we know that the fee goes up by $10 for each extra 100 flyers. So if we were to extend that to 500 flyers, which was what we were given in the question, we would see that it lines up with $60, and I've outlined that in red there. So if we extending the table of values would be the strategy. It says here, make sure you communicate the strategy you're using. So for Abby, we just used logical reasoning. For Craig, we extended the table of values, and then we read the table, and we see that Craig would make $60. For dollar from the graph, we can interpolate or read from the graph. We can see if we take a look at the graph, if we find 500 flyers, which is here, and then we read from the graph, so we're interpolating. So we go up to the graph, and then we go across here to the earnings axis, and we see that she would earn $50. So the approach for dollar would be to interpolate from the graph, and we get $50. For the equation, what we would do is we would substitute the value of n into the equation to evaluate it. So we call that substituting, or substituting and evaluating the equation, I guess we might say. So here's the equation that we were given: E equals 0.15 n plus 31, and n is the number of flyers. So n is 500 is what we're told. So if I replace my n with 500 and calculate, I get $106. So that's Bob's earnings. So that's how we would calculate the value of the dependent variable from each of the 4 different representations, from words, from table of values, from a graph, and from an equation. What's a bit more complicated is finding the value of the independent variable, or at least it is for the equation method. So let's take a look at that. So in the second part of this problem, what we're told is that now we're to assume that the amount of earnings is $88. So how, using these 4 different representations, would we figure out how many flyers would need to be delivered to make $88 in earnings? So we're told the value of the dependent variable, the earnings, which is going to be $88, and we have to figure out how many flyers would need to be delivered from that. So for Abby, again, we'd use logical reasoning. So we know she's going to earn $25 as a flat fee, so we can subtract that right away from the 88 to see how much she would have to earn by delivering flyers at 9 cents a flyer. So if we subtract the 25, we get $63. And then we would have to realize that what we need to do is divide the $63 by 9 cents, or $0.09, to make the units the same. And if we do that, we divide and we get 700 flyers. Again, we're using logical reasoning, but I think you might agree that it's a bit more complicated when we're finding the independent variable using the logical reasoning. Would we think to subtract this 25? Would we divide by 0.09? That requires quite a depth of thinking. So not as easy to find the independent variable from logical reasoning. For the table, again, we would extend the table of values, but this is not this $88 does not actually fall directly in the table of values. It falls in between 2 values. So I've extended the table down here, 600, 700, 800 flyers, and I've extended this column until we get to the $88. So the 88 is between here and here. It's much closer to 90, obviously, than it is to 80. So we know our answer is going to be much closer to 800 than it is to 700. And we can do some kind of like dividing in between here. We know that it's 4/5 of the way between 80 and 90 is 88. So 4/5 of the way between 700 and 800 would actually be 780. So we can figure that out from the table of values. We could estimate the value, or we could use some proportional reasoning to figure out exactly how far it would be in between the values. From the graph does not extend to $88 on the vertical axis. If I had this graph on graph paper, though, here's my graph, it only goes up to $50. But if I had this on graph paper, I could extend it up to $88. So just continue this axis up here and extend the number of flyers across and sort of see where it intersects. So I'd need to do that on graph paper if I was going to do it. So I could extend the line as shown here once I've extended my two axes and then read from the line. Another way of doing it would be to find the growth rate from the graph and then use that. So if we take a look here, we can see that every 100 flyers it produces $10. This is a direct relationship. It starts at 0 on both axes, so it is a proportional or direct relationship. So it's not too difficult to do that way. So we can say each 100 flyers results in $10 more earnings, or that you're getting 10 cents per flyer. And then if we use that growth rate, then it's a little easier to figure out how much the number of flyers would be. For $88, we would need 880 flyers. So we can find it from the growth rate from the graph, as I just showed you, or we can continue the graph line and then read it by extrapolation from the graph. For the equation method, we need to use this process again of reverse operations to isolate the independent variable, and this is something that's going to come in really handy when we get to the next unit on where we're looking at linear equations in more algebraic form, where we're going to isolate this variable. Like, that's going to be a fairly common technique that we use, so good to learn it now. So here's our original equation, E equals 0.15n plus 31. We have to isolate the n, and we're going to use reverse operations, and we're going to use the opposite of BEDMAS. So we're going to do the addition subtraction part first, and then the division multiplication part second. So plus 31 here, so the opposite of adding 31 is subtracting 31. So we're going to subtract 31 from this side, which will get rid of this 31 here, and we'll have e minus 31 on the other side as shown on the next line. And then we're dividing both sides by 0.15 to isolate the independent variable. So I divide this side by 0.15, I need to divide this side by 0.15 as well, otherwise the equation is no longer in balance. So then that gives me this equation here, which is an equation that represents the independent variable in terms of the dependent variable. So I can use that expression now and substitute the $88 in here for E. So replace E with $88, subtract the 31, divide by 0.15, and I get 380 flyers for my independent variable. So there are methods to find both the dependent and the independent variable for all four representations of linear relations, be it in words, be it an equation, be it a table of values, or be it a graph. So that's kind of the last thing that we would need to find from a linear relation.